Hi class, welcome to our class in Chemistry 2. This is Sir Alex, and today we'll be discussing our fifth lesson, and today we'll be discussing all about heating and cooling curve. The goal of our lesson for today would be for us to be able to determine as well as explain what is heating curve and cooling curve of a substance. So let's begin by talking about what is heating curve. Heating curve is basically a plot or a graph that we use to identify the temperature, uh, the temperature increase across a period of time. Meaning we are adding heat onto a substance and then we measure the temperature over a period of time. This is very useful when we want to measure the amount of energy the system or the substance absorbs as we add heat onto the substance. When we talk about energy, I also want you guys to imagine it as heat. So when I say energy, you can interchangeably think of it as heat. So as we add heat onto the substance, that heat is actually absorbed. Also, this is very useful in identifying at what temperature the substance changes its state, meaning at what temperature does the substance change from liquid or from solid to gas or from solid gas to liquid. So we have an example of a heating curve graph right here. This heating curve is actually a heating curve for water or H2O. So I want you guys to think that or remember that. So when we talk about this heating curve, it is the heating curve of water. What is interesting is that whatever the substance is, the shape of the heating curve is usually very similar, albeit it is at different temperature and at different times. Okay, so in this section right here, you can see that we are measuring the temperature. In here, we can use it to measure the heat, or also we can use it to measure time. So there are different parts of heating curve that we will be talking about today. And before I begin talking about those parts, I'm gonna first give points at each varying stages. So this is point A and point B. This is point C, D, E, and F. And then we'll be discussing each segment of the heating curve, what is happening at each line or at each point. Okay, so what I want you guys first to realize is there are two flat lines or plateaus. Okay, so there are two plateaus happening in heating curve, and you can see them at segments B and C and segment D and E. Later, we'll be discussing what is happening at this plateau. Another thing that I want you guys to see is that as we add more heat onto the system, the temperature increases. And that's how we know that this is a heating curve. Okay, so first let's talk about segments A, B. What is happening at segments A, B? At this point, the particles are solid. So in this case, since this is water, this is ice. So you can see the particles at this top right here. The particles are all compact, meaning they are in solid form. And the temperatures is at negative 40 to 0 degrees Celsius. And we know that anything below 0 degrees Celsius, the temperature of water is, or the state of water, or H2O, is ice. So meaning, depending on what substance that you are looking at, this can be higher or lower. Okay, what else is happening as we look at sections A and B? So we are adding heat, okay? So I want you guys to imagine that as we add heat, the temperature increases. And we know that as temperature increases, the particles of the substance increases their kinetic energy. So what is also happening is that the kinetic energy of the particles is increasing. So meaning they are moving faster and faster. So they start vibrating and shaking, and the particle starts moving faster and faster. So the heat that is being added from sections A to B is being used to increase the temperature. So what that means is that also the potential energy is constant at this point. Okay, so those are the things that I want you guys to remember at points section or segments A to B. And this will happen, the temperature will increase until it reaches point B. Point B is what we call the melting point. Okay, so this is the melting point, point B. So what this means is that the temperature is enough that it starts to break apart the intermolecular forces holding the particles together. So this is also the start of what we call phase shift. So at number 3, at segments BC, what is happening is a actually phase change. In this scenario, the phase change is melting. Okay, so during this scenario, the heat that is being added is not increasing the temperature. So the temperature is constant, right? So what that means is that the kinetic energy is also constant. It is constant because the potential energy is increasing at this point, because the heat that is being added is being used for phase change, meaning we are changing the structure of the we're changing the structure of the substance. In this case, both solid and liquid exist in this scenario. So the heat that is being added is what we call the heat of fusion or delta H fusion. This is the heat that is being added in this case. So this will continue to happen as we keep adding heat until it reaches point C. At point C, the temperature then will start to increase again. So number 4 is sections or the segments CD. As you can see here, the temperature is increasing at CD again. So meaning the kinetic energy of the particles are increasing and the potential energy is again constant in this scenario. What is happening here is that the heat that is being added is only increasing the temperature. It's not changing the phase of the substance. Okay, so as you add heat, the temperature again increases until you arrive at point D. So point D is what we call the boiling point. So what that means is that the particles are moving fast enough in liquid phase that they start to break off again their intermolecular force, changing the liquid. So this is only liquid state. Okay, so they start to change, the liquid particles start to change to gas. So in this case, when we arrive at DE, the particles present are both in liquid and gas form. Okay, another interesting thing that I forgot to mention about is at point C, all particles are now liquid. So there's no more solid at point C. Similarly, at point E, sorry, Similarly, at point E, all particles, oh, we're still at, uh, oh, sorry, we're still at D. So later I'll discuss what's point E is. So, okay. So point D is again is the boiling point, and we know that the boiling point of water is at 100 degrees Celsius. So point D should be at 100 degrees Celsius. Again, depending on what substance you have, the temperature could be lower or higher. Okay, so when the substance reach boiling point, it enters the section DE, wherein phase change occurs again. The phase change happening here is what we call evaporation. And both gas and liquid particles is present at this point. So as I'm similarly on this BC, what is happening on DE is that the temperature is constant. So meaning the kinetic energy of the particle is constant, but the potential energy is increasing. So whenever the potential energy increases, the phase change happens in heating curve. So until it reaches point E, wherein all particles, like I mentioned earlier, is that all particles are now gas, in gas form. So there's no more liquid at point E. Okay, so all particles are now in gas form. So when that happens, when it finally changes all the liquid particle into gas, the temperature increases again. So uh, segments E to F, temperature starts to increase again. So meaning the kinetic energy increases again, while the potential energy also is constant. Okay, so those are the different sections of a heating curve and what is happening on heating curve. And I forgot to mention during sections DE, also during section DE, is that the heat that you are adding is what we call the heat of vaporization or HVAP. So because the heat that you are using is converting all the liquid particles to gas particles. Similarly here, the heat that you're adding is converting all the solid particles to liquid particles, making it a heat of fusion. Okay, so I hope that's clear on what the heating curve is and what is happening on all the heating curves. Okay, so how is this different from a cooling curve? So cooling curve is again, it's also a plot or graph wherein a substance is subjected to decreasing temperature against time. So in this scenario, what is happening is that the cooling curve, instead of increasing the temperature is decreasing. That's why it's cooling. What is also happening is that the heat or the energy is being released instead of being absorbed in cooling curve. And this is very important to actually measure the amount of energy the substance or the system release as we cool the substance. And also we can see here at what temperature again a phase change occurs. So here's an example of a cooling curve. Okay, so as you can see, the drawing is basically the same as heating curve, only it's going down, or the direction is going, um, instead of up, it's going down. This is because the temperature is decreasing. So again, this is H2O, and to discuss this again, we're gonna mark them points A to F. So this is point A, this is B, C, D, E, and F. Okay, so at points A to B, as you can see, the temperature is decreasing. So meaning the heat is being released. As heat is being released, the temperature decreases. So what is happening here is that the kinetic energy of the particle is actually decreasing, but the potential energy is constant. So as it moves from A to B, the temperature decreases, the kinetic energy decreases, the particle slows down, but the potential energy of the particles is constant. Then we move to PC, where in this section, what is happening is that the temperature is constant, but so meaning the kinetic energy is also constant. But the difference is that the potential energy is now decreasing. And what happens is that another phase change occurs. So like I mentioned earlier, whenever there is a change of phase, whenever there is an increase or decrease of potential energy, a phase change will occur. Only in this scenario, the phase change that is happening is condensation. So what that means is that this section right here, uh, there are both gas and liquid present in the substance. Okay, and point B is actually the condensation point. It is the point wherein uh, also B and C, there's only steam, so there's only gas presence at B and C. So as we move from point B entering point B, the steam or the gas start to become liquid. Okay, so gas to liquid. So both B and C, both gas and liquid is present until it arrives at point C. At point C, all particles are now liquid. So now that a phase change finally finishes, so all the gas particles are now liquid at this state. What the system would do is to continue to decrease the temperature again. So at section CD, temperature again decreases. So when the temperature decreases, the kinetic energy decreases. So the particles start to slow down again. So the heat is being released again to decrease the temperature. Moreover, the potential energy is once again constant because there's no phase change. Okay, and this will keep the temperature will keep decreasing until it arrives at point D. And point D is what we call the freezing point. Because at sections CD, all particles is liquid, and the particles are slowly slowing down as the temperature decreases until it reaches freezing point, wherein phase change. Uh, this was yes. phase change again occurs at D to E. So the energy being released is not being is causing not to decrease the temperature but to phase change. And this phase change is what we call freezing. So it's changing the structure of the liquid particles for them to become solid or for them to solidify. Okay, until it reaches, oh, so at DE, at phase change, both liquid and solid particle is present. So at point E, all particles are now solid. So there's no more particles to phase change. What happens then is that it again starts to decrease temperature. So at section or at segments E to F, temperature again decreases, meaning the kinetic energy is decreasing, but the potential energy is constant. Okay, so also at DE, PE is decreasing, kinetic energy is constant. Okay, so at this point, what are the heat being called? They are the heat that is being released here is still the same as the heat that is being absorbed in heating curve. So we still use delta H of vaporization here. So delta H vaporization is equals to delta H condensation. So the heat here is delta H vaporization, and for here it's still delta H fusion. Okay, so that is what is happening for cooling curve. So in summary, so heating curve is what we call the endothermic because energy is being absorbed. So the phase change that is happening here is melting, evaporation, and sublimation. We did not discuss about sublimation, but for sublimation, the curve is actually just a straight line. Unlike for melting and evaporation, where the curve is not smooth, there are plateaus. For sublimation, there are no plateaus. It's a straight increase in temperature. Okay, so also different parts from A to B, kinetic energy increases, potential energy is constant, and then it arrives at B wherein it starts to melt. So B is melting point, wherein the kinetic energy is constant and the heat of fusion that is happening here is increasing the potential energy, causing phase change from solid to liquid until it reaches point C wherein all the particles are now liquid. So the heat that is being absorbed is again increasing the temperature until it reaches point D where it is the boiling point. And the particles start to escape and becomes liquid to gas. And the particle is phase changing because the potential energy is increasing, but the kinetic energy is constant. So the energy of vaporization that is being used here is being used for phase change until it reaches here point E where all the particles are now gas, and when all the particles are gas, again the heat that is being absorbed will again finally increase the temperature. And for cooling curve, it's what we call an exothermic system because the energy is being released in the system instead of being absorbed. And the phase change occurring here is what we call condensation, freezing and solidification, and deposition. So for condensation and freezing, the curve is not smooth. There are some plateaus, but for deposition, the curve is actually just a straight line. So cooling curve is basically the opposite of heating curve. We start at a higher temperature, and then the beginning phase of our substance is gas, and then as energy or heat is being released, the kinetic energy is actually decreasing, but the potential energy is constant. And then until it reaches again the time that's a boiling point, or the condensation point, wherein the gas starts to change to liquid. So the heat that is being released here is causing the potential energy to decrease, resulting in gas turning into liquid, and the kinetic energy here is constant until it reaches point C, wherein all the particles here are now liquid. So after all the particles changes from gas to liquid, the heat that is being released is again being used, is again resulting for the decrease of the temperature. And when temperature decreases, kinetic energy decreases, the particles again starts to slow down, but the potential energy is constant because there's no phase change until it reaches point D, wherein this is the freezing point, or the basically the same as the melting point, wherein the release of energy is resulting for the change of liquid particles to become solid. So they start to solidify or freeze. So what is happening again? The potential energy decreases, but the kinetic energy is constant until it reaches point E here, wherein all the particles are now solid, and what happens is it will just continue to decrease the temperature. So that is the summary of heating and cooling curve. So the next part is, how do we measure the amount of energy? Okay, so when we want to measure the amount of energy being absorbed or being released, these are the things that we need. One is that we need the mass of the substance. So we usually use grams or mole. Later in our next subject, I'll be teaching about moles and other way to measure particles or solvents. Okay, but as you guys remember, this is the first thing that we need is the mass of a substance, usually in grams or moles. We also need the heat capacities of a substance, and the units we use for heat capacities is joules per gram degrees Celsius, and they are different for each state. So meaning if you have water, the heat capacity of water when it's solid is different from when it's liquid, and it's also different from when it's solid. Similarly, the heat capacities of a liquid water is different from the heat capacities of, let's say, an alcohol. So each state is different, but it is usually given in the problem. So let's just make sure to look for the heat capacities given in the problem. What you also need is change in temperature. And what you need to remember is the two heat of fusion and heat of vaporization. So heat of fusion, if you guys remember, is the heat that changes, uh, or the heat that is present on the plateaus of the um, curves. So these are the flat lines, the B, C's, and I think it was the DE. Okay, so the heat diffusion is usually the heat that makes the solid turn to liquid or liquid to solid. And the heat of vaporization or delta H vaporization is usually the heat that changes liquid to gas or gas to liquid. And both of these are usually given in the problem. And their units is usually in joules per mole or joules per gram. Okay, so what are the equations that we need in measuring the amount of energy? Do not get confused, but there are five um, equations that I want you guys to remember. So they're written here on the top. So when we are measuring AB, the amount that is being absorbed or released, in this case, this is heating curve, right? So the heat is being absorbed. But even if this even if this is a cooling curve, you still will use the same what do you call this equation. You are just solving the total heat being released or being absorbed by the system. And this is the equation that you need. So when we use Q, it usually means the heat. Okay, so for AB, what you use is Q is equals to M CS, but for solid and delta change, or the delta time, or not time, temperature. Okay, so M is basically the mass of the substance. CS is the heat capacity, but this time this is the heat capacity for solid. So when the substance is at solid. Again, the heat capacity it is given, but please identify whether what the heat capacity is. Is it in solid, liquid, or gas? Because they're very different even on just one substance. And then delta change in time is basically how much temperature is changed. So meaning for heating curve, it's usually here. Uh, and so this is the initial temperature, and this is the final temperature. So usually delta T is equals to temperature final minus temperature initial. Okay, the same thing for cooling curve. So only for cooling curve, this becomes your initial, then this becomes your final. That's why for heating curve, usually the temperature is negative. But for heating curve, temperature is usually positive. It is positive because you're increasing temperature. So from here, let's say this is negative 60. So, and this is 0 degrees, right? So for here, so delta temperature is equals to your initial is, or your final is 0 minus negative 60. So your temperature is actually positive 60. But for cooling curve, your initial temperature is 0 minus, and then your final your initial temperature is 0 and your final temperature is negative 60. So delta T for heating curve would be negative 60 minus 0. It's negative 60. So that's why the temperature for cooling curve is negative, but for the temperature for the heating curve is positive. Okay, but this is the equation that you use. For section B, C, the equation that you use is Q is equals to Q is heat. Okay, this is heat. But for BC, what you have to use is only the mass of the substance multiplied by the delta H of fusion. So the heat of fusion of the substance. So those only two. And the heat of fusion is usually given. Quite simple. Okay, so you don't have to measure the temperature because as you can see, there's no temperature change anyway. So for CD, what you need to use again is mass, heat capacity, but this time in liquid form, and again delta temperature. So the change in temperature, There's change in temperature because for heating curve, the temperature increases. For cooling curve, the temperature decreases. So you need the mass, heat capacity, but for liquid, and change in temperature. So for D and E, so you can see there's no change in temperature for both the heating and cooling curve. So what you just need to use is the mass of the substance multiplied by the delta H of vaporization, or the heat of vaporization, or the heat needed to vaporize the substance. Okay, so again, this is given. You just have to make sure to find the correct heat of or item or number given. And lastly, for E to F, again, there's change in temperature. So what we have to use is mass multiplied by the heat capacity, but this time it's in gas form, and then the change in temperature. Okay, so this is the what do you call this? These are the uh, equations that you use to measure the different heat or the amounts of heat being released or being absorbed by the system. So these top equations right here. So let's try a problem on how to find them. So sample problem. Calculate the total amount of heat absorbed in kilojoules. So this time we're not talking about joules but kilojoules. So we have to convert our answer later. When we have 2 moles of ice at negative 30 degrees Celsius, and then it is converted to steam. So ice is solid, steam is gas, and we want to change the temperature from negative 30 degrees to 440 degrees. And then the required heat capacities and specific heats for water. So we're talking about water as our substance is given on the table. So again, these are usually given on the problem, but you just have to make sure that you use them on the proper equation. So what we're gonna do is we're gonna solve the problem. Okay, let me just pull this up and then we're gonna solve the problem. Okay, so this is our problem. Okay, so I read the problem earlier. So how are we going to solve this? So what we're going to do first is let's write our given. So the first given is that we have 2.0 moles of ice. In this case, we have a solid H2O. So our first temperature, the initial temperature, is equals to negative 30 degrees Celsius. And then we are trying to convert things to a steam. So our final temperature is 140 degrees Celsius. Okay, but also think that these are not the immediately final, initial and final. Late realize that since this is water, there are varying temperatures that we have to consider as well. And then the required heat capacities and required the delta H fusion and delta H vaporization are also given. So what is being asked in this question is to uh, measure the total heat or measure the Q total. So how are we going to do that? So we have to use all our 5 formulas. Remember the for heating curve, the graph usually looks like this, right? And each points A, B, C, D, E all have different uh, equation that we have to use to measure the total heat or the total energy absorbed by the system. So for A, we have to use, so let's go to our solution. So the initial temperature here is negative 30 degrees Celsius, and the final temperature is negative 140 degrees Celsius. So we have to solve for all this section right here to get the total heat. So solution. So for part A, we have to use Q is equals to M, heat capacity in solid, multiplied by the change in temperature. So we begin by first getting the um, mass of our substance. So we have to get the mass of our substance. So we have 2.0 mole of ice. We know that ice is actually H2O, correct? So we have to do is to change this mole into a gram. So later in our class, I'll show you how to do that. But for now, we add 2.0 mole of ice is actually equal to 36 grams of ice. I'll show you how to do that on our next lesson. But so on your homework, I'm not gonna make you guys do this. I'm gonna give you these, so don't worry about that. Okay, so for A, we have to solve the heat for A. Since we know the mass, so 36 grams of ice multiplied by the heat capacity of the solid ice. So this is the heat capacity. It's 2.06 joules grams per degree Celsius. And if you guys remember, this point right here is what? The melting point, right? The melting point of water is 0 degrees Celsius. So the initial temperature is actually negative 30 degrees, and the final temperature is 0 degrees Celsius. So 0 degrees Celsius, because we're only talking about A here. So this is only A. So our temperature is only until here, not the full E yet. So this is, so if you guys remember, this point right here is the melting point. So we go from this line to this line only. This is A. So the initial temperature is negative 30 and the final temperature is 0 degrees Celsius. So meaning this is T temperature final minus temperature initial, which is negative 30 degrees Celsius. So grams is cancel, degrees Celsius is also cancel, and this would actually give us 2224.8 joules. And since we are looking for kilojoules, we just have to change these joules to kilojoules. So we have 1 kilojoule per 1000 joules, because 1 kilo is equals to 1 kilojoules. 1 kilojoules is equals to 1000 joules. Cancel joules, so we basically have 2.23 kilojoules of heat for A. Okay, now let's move to B. So we are now talking from point B to point B. And is since you guys, if you guys have to remember now, the equation that we use is basically Q is equals to M delta H of fusion. So we know that the mass of our 2 moles of ice is 36 grams, and then multiplied by 6.01 kilojoules per mole. So this is easy. A little mistake there, so let's just erase this. So you can see they gave us for the delta heat of fusion, it's actually 6.01 kilojoules per mole. So they gave us mole here, so we have to use the mole of the substance, 2.00 mole, because in order to cancel this, if we use grams, we cannot cancel it. Okay, and this is equal to 15.1 kilojoules. So this is our second, let me just write that properly. So this is 15.01 kilojoules. So this is our answer in B. Okay, so now, so let's talk about this portion right here, our third part. And we know that in C, we have to use Q is equals to the mass of the substance, heat capacity, but this time in liquid form, multiplied by the change in temperature. Okay, so multiplied by the change in temperature. So the mass of the substance is 36 grams, and the heat capacity in liquid form or water is 4.18 joules per gram degree Celsius. And the difference in time is that we know that this is 0 degrees Celsius. And we know that this point is the boiling point of water. And the boiling point of water is 100 degrees Celsius. So 100 degrees Celsius is the TF, or the final temperature, minus the initial temperature, which is 0 degrees Celsius. So let's cancel the grams and the temperature, and this would give us 81.4 kilojoules. I already converted it to oh no, oh wait, I made a mistake. Okay, so this should be, if you guys use calculator, this actually should be 12.0 kilojoules, and this one is the 15. Sorry about that. Oh, this one should be the 15.01 15.1 kilojoules. Okay. Okay, the part we have to use Q is equals to mass multiplied by delta H of vaporization. Okay, so again we have to use moles because they give us moles here, because they're equal anyway, right? 2 moles of ice is equals to 36 grams of ice. So 2 moles of ice multiplied by delta H of vaporization is 40.7 kilojoules per mole. Have to cancel mole, and this would give us 81.4, I think, 81.4 kilojoules. And lastly, for E, we are now talking about this part right here. So we know this is 100 degrees Celsius because this is the boiling point of water. And this is the final temperature given to us, which is 140 degrees Celsius. So the equation that we have to use is Q is equals to the mass of the substance multiplied by the heat capacity, but this time in gas, multiplied by the change in temperature, which is equals to 36 grams multiplied by 1.87 joules 1.87 joules per grams degrees Celsius multiplied by the change in temperature. The final temperature is 140 and the initial temperature is 100 degrees Celsius. So using calculator, this should give you 269.8 joules. Again, just convert that to kilojoules. 1 kilojoule is equals to 1000 joules. Cancel joules, and that would give you 2.69 kilojoules. So after getting all of these, we're not done yet. So what we just have to do now to get the total temperature is to add all of them. So the Q total is basically adding all of them. So we have 2.23 joules plus 12.0 kilojoules. This is kilo, sorry. Plus 15.1 kilojoules plus 81.4 kilojoules plus 12.69 or 2.69 kilojoules, and this would give us a grand total of 113.42 kilojoules. So that is our final answer. So how is this different if we use what we call a cooling curve? The only difference is that this number would be negative, because remember, for cooling curve, temperature in these equations is negative, so all the answer would be negative, and then you just have to add everything. So for this cooling curve, so the Q total for cooling curve in this same water or in this same substance, Q total should be equal to negative 113.42 kilojoules. Okay, so this would be negative 2.3, negative 12, negative 15, negative 18, negative 2.69. Add all of them is equals to negative 113.42. So that is heating and cooling curve. So I hope it's understandable. Sorry and apologize for the mistakes that I did, but I hope it's clear. And if you guys have any questions, Please do not hesitate to message and contact me. Thank you very much, and hope you guys have a great